So for today's discussion, we will do a review session for the second exam. So let us start with this first problem. So consider the polar curves C1, which is this cardioid, r equals 1 plus cosine theta. So it's this purple curve. And then C2 to be the circle r equals 3 cosine theta. So we have here the blue circle here. First, we want to find the Cartesian equation of the tangent line to C1 at the point where theta equals pi over 3. Okay, so we want the Cartesian equation. So we recall the conversion of polar curves to Cartesian, and we can convert this polar curve here to its corresponding Cartesian equation by using the substitution x equals r cosine theta and y equals r sine theta. And then our r here, it's 1 plus cosine theta. So we have here 1 plus cosine theta times cosine theta. And then for the y, we will have here 1 plus cosine theta sine theta. And if we simplify this, if we distribute the cosine or the sine here over the sum, we'll just have cosine theta plus cosine squared theta. Cosine squared theta. And for this guy, we have sine theta plus sine theta cosine theta. So why do we need this? Because again, we need a tangent line. We need the slope of the tangent line. And in terms of the Cartesian plane or the corresponding equation, the Cartesian coordinates, we have dy over dx. But this is just dy over d theta all over dx over d theta. So we have the y here in terms of theta, and we have the x here in terms of theta. So let us calculate the derivatives. So for dy over d theta, we have cosine theta plus, and then we apply product rule here. We have left. So sine theta, derivative of right, that's negative sine theta, plus for this, you have the right here, it's cosine theta, and then the derivative of left, which is also cosine theta. So that's for the numerator. And then for the denominator, we do the same thing. So here we have derivative of cosine, that's negative sine theta. And then here, get the derivative of cosine squared. So we have 2 cosine theta times negative sine theta. Right? So this is dy over dx in terms of theta. And we want the slope of the tangent line at the point where theta equals pi over 3. So we have dy over dx evaluated at theta equals pi over 3. So in the numerator, we have cosine pi over 3. That's just 1/2. And then here plus or minus, because we have minus here, sine pi over 3. That's square root of 3 over 2. Square root of 3 over 2. But we square it because this is sine times sine. And then plus, and then again cosine pi over 3, that's 1/2. So we have 1/2 quantity squared. And in the denominator, we have negative sine pi over 3, which is square root of 3 over 2. And then we have minus here. So minus 2 times cosine pi over 3, that's 1/2. And again, sine pi over 3, that's square root of 3 over 2. Now, if we simplify this, square root of 3 over 2 squared, that's just 3/4. And then we will have 1/2 minus 3/4, and then plus 1/4. 1/2 squared, that's 1/4. And then for the denominator, 2 times 1/2, that's just 1. So we just have negative square root of 3 over 2 minus square root of 3 over 2. So that's just square root of 3, negative. So denominator is not 0, but numerator here it's equal to 0. 1/2 minus 3/4 plus 1/4. So this is the slope of the tangent line, and therefore the tangent line is horizontal. Therefore, the tangent line has equation TL at the point where theta equals pi over 3 is, so we just need the y value because the tangent line is horizontal. So we need the y value at theta equals pi over 3. So in here you have square root of 3 over 2 plus square root of 3 over 2 times 1/2 here. So if you simplify this, this is square root of 3, or this is 3 square root of 3 over 4. 3/4 of square root of 3 over 2. Okay? Sorry, 3/4 of square root of 3. So this is the equation of the tangent line. So if you can see it here, or if you try to find that angle equals pi over 3, it's actually at this point. Okay, so let me use this purple. So at this point, and this is that line. This is the tangent line at that particular point. So this is the point, this is the tangent line there. And that's y equals square root of 3/4 of square root of 3. Okay. So that's for the first problem here. Let's do the second problem. So we want to find, or we want to get the polar coordinates of the points of intersection of C1 and C2. So this is straightforward. We just need to equate the equations for C1 and for C2. So we have 3 cosine theta equals 1 plus cosine theta. So this is now 2 cosine theta equals 1, or cosine theta equals 1/2. Okay? Now, what is the domain of these curves here? First, for the cardioid, let us take the domain 0 to 2 pi. Okay? So this cardioid will be drawn once on a 2 pi interval. So at theta equals 0, we have here 1 plus cosine 0, so that's 2. So this is where theta equals 0 is. And then at theta equals pi over 2, so this angle here, we have cosine pi over 2, that's 0, so r equals 1, so it's this point. At theta equals pi, cosine pi, that's -1. So r equals 1 minus 1, that's 0. So this is that point. So from this point going to this point, that's from 0 to pi. That's half of your cardioid. And then from pi to 2 pi, that's the second half of your cardioid. Okay? On the other hand, for the circle, r equals 3 cosine theta, you only need the interval 0 to pi in order to draw this circle once. Okay? And you can check that easily. So when theta equals 0, that's r equals 3, so it's this point. When theta equals pi over 2, cosine pi over 2, that's 0, so it's this guy here. Okay? And then when theta equals, where are we now? When theta equals pi, so this angle here towards to the left, when theta equals pi, cosine pi, it's -1, so r equals -3. So although the angle is towards to the left, r equals -3, so it will go back to that side. So from 0 to pi over 2, you have the semicircle, and then from pi over 2, you have the other part of the circle. So the lower semicircle here. Okay? But notice, this guy here, if we only consider 0 to pi, the equation cosine theta equals 1/2 will only give us, okay, will only give us theta equals pi over 3. So this guy here is on the interval 0 to pi. Okay? Theta equals pi over 3. Okay? So this point here, the point of intersection here, it's at the point where theta equals pi over 3. But what about the other guy here? So what we're going to do is, well, we can draw a second circle, which means that we will inherit the domain of the cardioid. Okay? The domain of the cardioid. We'll get the domain of the cardioid and use it as the domain of our circle. So 0 to pi and then pi to 2 pi. Okay? And we will see that on the interval 0 or on the interval pi to 2 pi, okay? Pi to 2 pi, we will obtain this point here. Okay? We will have theta equals 5 pi over 3. Okay? So we have these two values of theta, which is consistent with the sketch of the graphs here. We have this point and we have this point. Okay? And of course, just to see this clearly, we have this angle here. This is your pi over 3. Okay? This is your pi over 3. And then this guy here, this is your, so let me use another color. So this guy here, that's your 5 pi over 3. Okay? So if we want the polar coordinates, we can just use theta equals pi over 3 on C1 or even on C2. But on both occasions, pi over 3 or 5 pi over 3, we have cosine theta equals 1/2. So we can use this C2, and therefore the coordinates, the polar coordinates will be 3/2, comma, pi over 3. And then for this guy here, Still, we have 3 halves, but the theta is 5 pi over 3. So these are the points of intersection in polar coordinates. Okay? Any questions? Then for the third problem, we want to set up the integrals that will give the area and the perimeter of the shaded region. So let's copy this guy here. So what we can do, we know that for this, we have here, okay, at the point where theta equals pi over 3. And of course, at this point, we have, okay, we have the point where theta equals 5 pi over 3. But the shaded region here, it's symmetric, okay? It's symmetric on the angle theta equals 0. So we can just compute for the area and the perimeter on this shaded region and then just multiply it by 2. Okay? So for the area, this is twice of something. But what is this something? So observe for this part here. So before pi over 3, we have this part up to this part only. So up to the cardioid only. So from 0 up to pi over 3, we just use the cardioid. Okay? So this is equal, this part here, the area here, that's equal to 1/2 integral from 0 to pi over 3. And then cardioid r squared, correct? So you have 1 plus cosine theta, quantity squared d theta. So you have this shaded region here. But from pi over 3 up to this particular point, okay? So this guy here, the boundaries, okay? Or the boundary is just from the circle. So this time you use the circle. But this guy here, it will be from pi over 3 until this particular point of the circle. And we said earlier that this will be at the point where theta equals pi over 2 for that circle. Therefore, we have here plus 1/2 integral pi over 3 until pi over 2. And then you have the circle. 3 cosine theta squared d theta. And that will be the area or a setup of the integral that will give us the area. And then for the perimeter, I guess you have the integral or the limits of integration already. For the perimeter, you have the cardioid from this point up to this point. And then from this point up to this point, you have the circle. Okay? So for the perimeter, again, we use symmetry. It will be twice. And then we have the integral from 0 to pi over 3 of the square root. So recall the formula for the perimeter. We have r squared. So 1 plus cosine theta squared plus dr d theta squared or r prime squared. So we have negative sine theta squared d theta, plus we have the integral from pi over 3 to pi over 2 of the square root. We have your 3 cosine theta squared plus negative 3 sine theta squared, and then you have d theta. And then we close the bracket. So this will give us the perimeter of the shaded region, or yeah. Questions? Okay, let's proceed to our next problem. Let S be the surface with equation z equals x squared minus 4y squared. First problem, we want to identify the type of the quadric surface S. Second, we want to identify the trace on S on the coordinate planes and on the planes x equals 1, y equals 1, z equals 1, and z equals negative 1. And then we sketch the graph of S. So for the type, you can just try to observe this. When x equals 0, you have z equals negative 4y squared, that's a parabola. When y equals 0, that's z equals x squared, that's another parabola. And then when z is positive or negative number, you will get hyperbola. So you have one hyperbola and two parabolas. Okay, so the type will be hyperbolic paraboloid. Paraboloid. Okay, so remember where you put your ik and your oid. The ik will be the one with the lower number of conic. Okay, and then the oid, that's for the higher number of conic. I hope you get what I mean. So two parabola, one hyperbola. Okay. For number 2 here, the traces on coordinate planes. So let's start with, let's start with x equals 0. When x equals 0, you have z equals negative 4y squared. So let's see. Let's try to sketch that. So this is your z, this is your y, and then, oops, I need the lower part of z, and of course the negative side of y, because anyway, this is a parabola. If this is the orientation, this is a parabola opening downwards. So let me rewrite the axis or redraw the axis. So you have your z here, you have your y here, and then the parabola will be something like this. Okay. Next, we have say y equals 0. Y equals 0. So when y equals 0, you have z equals x squared. So z equals x squared. And then for the orientation, let me draw it like this. So this is your z-axis, and then this is your x-axis. Okay. Of course, the arrowhead that points to the positive side of your axis. So this is the positive side of x. That's the negative side of x. Okay. And then we have z equals x squared. So the parabola will be something like this. Okay, so you are here. For example, you are here, okay, and then you are looking at that direction. Okay, and then when z equals 0, so when z equals 0, okay, of course we will get x squared minus 4y squared equals 0, but this is just x minus 2y and x plus 2y, x plus 2y. So you will get two lines, okay? Now, so what orientation was I using before? So let us use this orientation. So this is your x, and then this is your y, okay? So this is positive 1, this is negative 1, this is positive 1 for y. So that's negative 1 for y, this is negative 2 for y, this is positive 1 for y, this is negative 2 for y. So what about the two lines? So when we can have y equals 1, so we need x equals 2, we need x equals 2 and negative 2. So say this is negative 2. So when x equals 2 and y equals 1, we have 0. So x equals 2 and y equals 1, we have that 0. So this guy here, and then this guy here. Up here, we have this guy here and this guy. So we can draw this imaginary rectangle here. Of course, assume that I have the correct scaling here. Okay, and then the two lines will be something like this. Correct? Oops. So this is one of the two lines, and then the other, so we have this. The other line will be something like this. Okay? So we are somewhere above, okay? We are at the point on the z-axis. So we are looking downwards in here, okay? So that's for z equals 0. For z equals 1, we need that. For z equals 1, we will have the hyperbola x squared minus 4y squared equals 1. Okay? So we have, again, the x and the y axis. And this is hyperbola. Or we can rewrite this as x squared minus y over 1/2 quantity squared equals 1. So it's easier to visualize the hyperbola. So in here, we have the x-axis in here, and then we have the y-axis in here. So this is y, this is x, okay? And we are on the plane z equals 1. Take note of that, okay? So just like before, we have x here, 1 unit for x, negative 1 unit for x, 1 unit for y, negative 1 unit for y. But we need only y equals 1/2 and negative 1/2. So if we try to draw the imaginary rectangle, so we just have that 1/2. Okay. So we have this smaller rectangle. Okay. And let us try to draw the axis of the asymptotes of the hyperbola that we will draw. Okay. Since the positive side is for the x squared, the branches of the hyperbola opens towards the x-axis, correct? So the hyperbola for this will be something like this guy here. Then here you have something like that. Okay. And then finally, for z equals -1. So when z equals -1, we will have the equation 4y squared minus x squared equals 1. Or we can rewrite this again as y over 1/2 quantity squared minus x squared equals 1. So very much similar to this, except that now the hyperbola, the branches of the hyperbola opens towards the y-axis. Okay? So let's have that. This is your x. This is your y, positive y in here. This is positive 1x, negative 1 for x, positive 1 for y, negative 1 for y. So again, we have a rectangle here, the same size as the one in here, okay? And then let's draw the asymptotes of the hyperbola in here and then in here. And then now the hyperbola will be much wider, okay? Okay? Now, keep in mind, this guy here on your three-dimensional space, this guy here is above than this guy here. In fact, comparing these three sketches here, this is the one on top, and then this is on the middle part, and then this is on the lower part. So now, if you combine all of these sketches or traces, we can now sketch the graph of our surface. So we have here the z-axis. This is the y-axis. This is the x-axis. So x here, y here, and then z here. Okay. And then let me draw some the negative sides of everyone. So this is the negative z. This is the negative x. And then this is the negative of y. So for this guy here, we have this parabola. So let me draw something like this. And then somewhat there, I'll just draw this as dashed line. That's on this part here, it's on the back side. Right? And then this guy here, this parabola here, we have something like this here and then this here. And then if you look at this is above the xy plane. This is positive z. This is also positive z. So for z equals 1, we have this hyperbola. Okay? So we have that hyperbola. So we will have something like this here and then this guy here. Okay? And then the other branch of the hyperbola, we have something like that here and then this guy here. Correct? So this hyperbola, they are all on the z equals 1. I think let me adjust this part here. Okay. So here we have something like this. And then for this guy here, this is z equals -1. This tip here, if we call it a tip, it's below the xy plane. So this is -z. So the graph will be something like this guy here. Okay. Or let me, yeah. So in here, okay. And of course, for this part, you have something like, okay. So if we continue drawing this, we will have something like this, okay. And then for this guy here, we will have something like this. And for this guy, this part here, this is connected to this guy, okay. And then this guy here, they are connected. Okay. Can you imagine the saddle? Can you imagine the hyperbolic paraboloid? So that's the shape of your hyperbolic paraboloid. Questions? Okay. Next problem here, we have the vectors u, v, and w. So for the first part, we want to find the magnitude of 3u minus 5v plus w. Second part, we need the projection of v onto u. And the third, unit vector that is perpendicular to both u and w. So this is purely computation. So everything will be straightforward. So we have the magnitude of 3u minus 5v plus w. So this is equal to the magnitude. So 3 times u here, we have 3i hat minus 9j hat plus 6k hat. Then minus 5v. So minus 5 times I hat. This is plus. So still we have minus 5j hat. And then plus w. So we'll just copy this. Plus 2i hat plus 2j hat minus 4k hat. And then we close that. Then we simplify. We have here 3 minus 5, that's negative 2, plus 2, that's 0i. For this, you have minus 9j minus 5j, that's minus 14j. And then plus 2j, so we have minus 12j hat. And then here you have 6k minus 4k, so you have plus 2k. And therefore, magnitude will just be square root of negative 12 squared plus 2 squared. And this is what? Square root of 144 plus 4. And you can write the final answer as square root of 148. Okay. For the second problem, we want to find the projection of V onto U. So this is simply V dot U over magnitude of U squared times the vector U. So this is equal to, for the dot of V and U, we have 1 times 1, that's just 1. 1 times negative 3, so minus 3. And this does not have any k, so 0 times 2, that's 0. Divided by magnitude of U squared, so this is just 1 squared plus 3 squared plus 2 squared. And then the vector U, it's I hat minus 3j hat plus 2k hat. So if we simplify this, we have negative 2 divided by this 1 plus 9, that's 10 plus 4, so we have 14. Then I hat minus 3j hat plus 2k hat. And finally, we will get negative 1 over 7i hat plus 3 over 7j hat minus 1 or 2 over 7k hat. Okay? And then for number 3, we want to find a unit vector that is perpendicular to both u and w. So we can just get the cross product of u and w, and that will be perpendicular to both u and w. So we just need cross product u cross w. So this is the determinant. So I hat, j hat, k hat. And then for the u, it's 1, negative 3, 2. For the w, it's 2, 2, negative 4. So this will be, we have negative 3 times negative 4, that's 12, minus 2 times 2, that's minus 4 now. I hat minus quantity 1 times negative 4, that's negative 4, minus 2 times 2, so minus 4 j hat plus, for the k, 1 times 2, that's 2, minus 2 times negative 3, that's positive 6. So this is k hat. So if we simplify this, we have 8 I hat minus, oh, this becomes plus, correct? Plus 8j hat, then plus 8k hat. So this is perpendicular to both u and w. We need a unit vector. Okay. So let's just get the, we can get the magnitude of u cross w. So this is just the magnitude of 8i hat plus 8 j hat plus 8k hat. So this is equal to 8. You can factor out 8. Then you get the magnitude of I hat plus j hat plus k hat. That's just 1 plus 1 plus 1. So this is 8 square root of 3. And therefore, the unit vector, the desired unit vector will be u cross w divided by magnitude of u cross w. So this is what? 1 over square root of 3i hat plus 1 over square root of 3j hat plus 1 over square root of 3k hat. So this is the final answer. Questions? Okay. Next problem. We want to find the parametric equations of the line through the point 5, 0, negative 2 that is parallel to the planes x minus 4y plus z, 2z equals 0, and 2x plus 3y minus z plus 1 equals 0. So, parallel to these planes, it means that the line is perpendicular to the normal vectors of these two planes. Okay? So if we label this as our plane 1 and this guy here as our plane 2, we have pi 1. This is perpendicular to the vector 1, negative 4, 2. And let me label this as n1. Pi 2, this is perpendicular to the vector 2, 3, negative 1. Let me label this as n2. So our goal is to find a vector parallel to the line. Okay? But if we want that line to be parallel to the planes, then that vector must be perpendicular to both n1 and n2. And therefore, we just need again n1 cross n2. Okay? So we look at this, n1 cross n2. So this is n1, this is n2. We use this. We have negative 4 times negative 1, that's positive 4, minus 3 times 2, that's 6, comma. We have 2 times 2, that's 2, that's 4, minus 1 times negative 1. So this becomes plus 1, comma. And for this, we have 1 times 3, that's 3, comma. Sorry. minus 2 times negative 4, that becomes negative 8. So this becomes plus 8. So if we simplify, we have negative 2, 5, 11. So we can use this vector to be the vector parallel to the desired line. Okay? And then we use this point so that we will get the actual line we need. So the line, so the desired line has equations. So parametric, okay, parametric. So we have x equals x naught, that's 5. And then we have here minus 2t. Then we have y equals y naught, that's 0. Then here we have 5t. So I'll just write 5t over here. And then z, we have negative 2 plus 11t. So here t is any real number. Okay? Questions? So next problem here, show that the lines intersect and find an equation of the plane they determine. So looking at the two representations of the lines, you have the same parameter, t, 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 and here there's no parameter, it's just 0t and then t here. So when trying to find the intersection, the point of intersection of these two lines, okay, in the three-dimensional space, you have to use different parameters. So for the second line, instead of t, I'll be using s. Okay? And then you just equate the x's, the y's, and the z's. So for example, this is your L1, this will be your L2. The x part of your L1, it's 4t minus 1. This should be equal to the x part of the L2. And just like I mentioned earlier, I will use a different parameter for L2. So I'll use s. So this is 12s minus 13. The y parts, we have t plus 3. And this is equal to 6s. So 6s minus plus 1. And then the z part, we just have here 1 for the L1. And then for the L2, you have 3s plus 2. Okay? And then let me label these as equation 1, equation 2, equation 3. So from equation 3, we can easily get s. We have 3s equals 1 minus 2, which is negative 1. So s equals negative 1/3. So we can use now equation 2. We substitute s. So from equation 2, we have t equals 6s plus 1 minus 3. And then we substitute s equals negative 1/3. So 6 times negative 1/3. 1 minus 3, that's minus 2. And here we will have 6 times negative 1/3. That's negative 2 minus 2. This is equal to minus 4. We have the value for S and for T. We just need to verify that these values satisfy the first equation. So when T equals -4, S equals -1/3. So the question is 4 times -4 minus 1, is this equal to 12 times -1/3 minus 13? Well, on the left hand side, we have minus 16 minus 1. On the right hand side, we have 12 over 3, but we have negative, so minus 4 minus 13. And indeed, we have minus 17 on the other side also. So they intersect. So L1 intersects L2 at the point where you can use S equals -1/3 for L2, or you can use T equals -4 for L1. Let's just use T equals -4 for L1. So the point of intersection will be 17. We get that here. Actually, -17. For the Y part, this is -4. You put this on the other side. So -4 plus 3, that becomes -1. And then for the Z, it's just Z equals 1. So this is the point of intersection. And now, the equation of the plane they determine, we need to get the cross product again of the parallel vector to L1 and parallel vector to L2. Okay, so let me just finish this part. So L1, this is parallel to the coefficients of T here as components of the parallel vector. So you have 4, 1, 0, and let me call this as V1. L2 is parallel to 12, 6, 3. And let me call this as V2. So if we get the cross product of V1 and V2, we will get a vector perpendicular to both V1 and V2. And that will become, or we will use that as the normal vector to the plane. So V1 cross V2. So here you have 1 times 3 minus 6 times 0. So that's just 0, comma. Then here you have 12 times 0. That's 0, minus 4 times 3. That's -12. Then here 4 times 6. That's 24 minus 12 times 1. That's 12. So if we simplify this, we will have 3, -12, and +12. So this guy here, okay, this guy here is, or we can use this as the normal to the plane. We can get another point, or we can get a point on any of the line and use that to get the equation. Let's just use the point of intersection here. -17, -1, and 1. So the plane is normal, or that has normal vector. So the plane has normal vector 3, -12, 12 and contains the point negative 17, negative 1, 1. So the equation is you have 3 times x minus negative 17, so that's plus 17, minus 12 times y minus negative 1, so that's plus 1, plus 12 times z minus 1, and this is now equal to 0. So, we want to determine whether this vector valued function r of t given by this piecewise function is continuous at t equals 0. So this is straightforward. We just want to check whether the limit of r of t as t goes to 0 is equal to r of 0. So this is the condition we need to check. Well, limit of r of t as t goes to 0. So by definition, we just need to put the limit inside this guy here. So t approaches 0, t is not equal to 0, we use the first vector valued function here, okay, or the definition of the vector valued function when t not equal to 0. So this is just equal to the vector whose components are the limit of square root of t plus 1 as t goes to 0, comma, we have the limit of sine t over t as t goes to 0, and then you have the limit of e to the minus t as t goes to 0, and then we close this. Okay? And then, well, as t goes to 0, this is just square root of 0 plus 1, and it is well defined, and the limit is simply 1. And then in here, we recall a theorem from your Cal 1, okay? So the limit of sine t over t as t goes to 0, it's also 1. And then in here, you have e to the minus t. As t goes to 0, it becomes e to the 0, and e to the 0, that's equal to 1 also. And clearly, this is the vector 1, 1, 1. It's the value of r of t at t equals 0. So therefore, r is continuous at t equals 0. Okay. Next problem. Evaluate the definite integral from 0 to 1 of e to the 2t I hat plus e to the minus t j hat plus t k hat dt. So again, this is straightforward. So we'll just immediately put the definite integrals. So you have the integral from 0 to 1 e to the 2t I hat plus e to the minus t j hat plus t k hat dt equals. So the integral of e to the 2t dt from 0 to 1, that's just e to the 2t over 2 evaluated from 0 to 1 I hat. Then the integral of e to the minus t, that's minus e to the minus t Then we evaluate this from 0 to 1 also. J hat plus the integral of t, that's just t squared, over 2, evaluated from 0 to 1, and then you have your k hat. So evaluating each component here. So at 1, we have e squared over 2. And then at 0, we have e to the 0 over 2. So minus 1 over 2 I hat. And then here we have minus e to the minus 1. Then minus e to the 0, that's 1. And then j hat. Then plus at 1, here you have 1/2. And then at 0, you have 0. So 1/2 k hat. So this is the integral of this vector valued function from 0 to 1. So straightforward computation. Okay. Next problem here. So given r of t, the vector valued function e to the minus t, comma, cosine t, comma, sine t. First is we want to find the vector equation of the line tangent to the point 1, 1, 0. And then second here, we want to find the curvature and the radius of curvature of the vector valued function r at the point 1, 1, 0. So let's do the easy part first. So we want the tangent line. Okay. So for the tangent line, we need the direction of the tangent vector. Okay. But we just need to get the derivative of r. Okay. And the derivative will give the direction of that tangent line. So you have here r prime of t. The derivative of this, it's negative e to the minus t, comma, negative sine t, comma, cosine t. Okay? Now, we need the point 1, 1, 0. So first, we need to identify or we need to determine whether this point is a tip of the vector r at some value of t. Okay? But just observe, if you have here e to the minus t equals 1, the other one here cosine t equals 1, and the other guy here you have sine t equals 0. So that's your 1, 1, 0 on the right hand side. On the left hand side, you have e to the minus t cosine t sine t. But if you combine this, you will easily get that the value of t must be equal to 0. Okay? So we will use this t equals 0, okay, in our computation. So notice r of 0, this is indeed 1, 1, 0. Now we have your r prime here. We evaluate this at 0. Sorry, r prime evaluated at 0. So we will have negative e to the 0, that's negative 1. And then negative sine 0, that's 0. And then cosine 0, that's 1. So this r prime of 0 will be the direction of the tangent line. Okay? And of course, if we use the points 1, 1, 0 here, then we have the tangent line. at the point 1, 1, 0 to this curve here. Okay? So therefore, the tangent line has vector equation. So the tangent line has vector equation. Let me write it as x, y, z. This is what? We have the vector 1, 1, 0. That's your r of 0. Plus the r prime. It's negative 1, 0, 1 times the parameter t. Or if you combine them into a single, or if you put them into a single vector, we have 1 minus t, comma 1, comma t. So this is the vector equation of the tangent line. Okay? So far so good. Now, let's do the second part here. So we want to find the curvature and the radius of curvature of r at the point 1, 1, 0. So we want to solve for kappa, okay? And this kappa of t, it has two formulas. You can use your t prime of t, magnitude of this divided by magnitude of r prime of t, where here t prime of t, this is the unit tangent vector, okay, of r of t. But we can also use the following. We can use magnitude of r prime of t cross r double prime of t divided by magnitude of r prime of t cube. Okay? And I think this will be handy in our computation. So we already know our r prime. We need r double prime. Okay? So r double prime of t. So if we go back to the previous page, this is our r prime. So for the r double prime, derivative of this is e to the minus t. Derivative of this is minus cosine t. Derivative of this is minus sine t. So try to remember that. We have e to the minus t minus cosine t. The other one it's minus sine t. Okay? And then we want the curvature and the radius of curvature at the point 1, 1, 0, and we know this is when t equals 0. So we actually need the curvature at 0. Okay? So we just need to do to calculate the cross product here evaluated at 0, at t equals 0, and similarly for this. So this will be an easy computation. So for the r prime of t, let us recall that. R prime of t evaluated at t equals 0, we have negative 1, 0, 1. So negative 1, 0, 1 cross r double prime at 0, we have here 1, negative 1, and then 0. And then divided by magnitude r prime at 0. So this is negative 1, 0, 1. We get the magnitude of that and then we cube it. Okay? Cross product. Okay? Cross product here. Let me put this, or let me write the calculation here for the cross product. I, J, K. And then we have negative 1, 0, 1, 1, negative 1, 0. So this is equal to 0 times 0 minus negative 1 times 1. So this is just 1 I hat minus negative 1 times 0. And then minus 1 times 1. So negative 1 j hat plus. For the k, we have here negative 1 times negative 1. And then minus 1 times 0. So the cross product, it's just 1, 1, 1. So magnitude of 1, 1, 1 divided by, let's write the magnitude of this. We have square root of negative 1 squared plus 1 squared, and then we cube this. Okay? And then for the numerator, we have square root of 1 plus 1 plus 1. For the denominator, we have 2 square root of 2. And finally, we will have square root of 3 over 2 square root of 2. So you can write the curvature at this form. Or if you want to rationalize this, you will get square root of 6 over 4. Okay? So this is the curvature. For the radius of curvature, so rho, at this particular point, so rho of 0, this is just 1 over kappa of 0. Okay? So we just need the reciprocal of the kappa that we obtained here. This is equal to, let's get the reciprocal of this. You have 2 square root of 2 over square root of 3. So if you're going to rationalize this, you just need 2 square root of 6 over 3. So this is the curvature. Okay? Questions? Okay. For this problem, find an arc length parametrization of the curve. So we have here r of t that has the same orientation as the given curve and for which the reference point corresponds to t equals 0. So arc length parametrization. So first, let us determine the arc length. And if you recall, we need S. This is equal to the integral from some reference point up to some t, which is our variable. So this is S of t. So this is S of t. Okay. Integral from some reference point t sub 0 up to t of the magnitude of r prime of u and then du. Correct? So this is our r of t. This is equal now, since our reference point is t equals 0, we have the integral from 0 to t of the magnitude. So r prime, let me put this in angle notation. So this one, we have sine e to the t, comma, cosine e to the t, comma, square root of 3 e to the t. Okay? So magnitude of derivative of this is e to the t cosine of e to the t, comma, derivative of cosine e to the t, it's minus e to the t sine e to the t, comma, and then here square root of 3 e to the t. Derivative is the same, square root of 3 e to the t. Sorry, why am I using t? I have to use u. I'm using the dummy variable u. So let me change that. So in here, 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 and here. Oops. So they must be u here, u here, u here, u, and u. And then, of course, the variable of integration, it's du. So we have the integral from 0 to t. We have the square root of e to the u cosine e to the u squared plus minus e to the u sine e to the u squared plus square root of 3e to the u quantity squared and then du. And if we simplify this, so 0 to t, integral from 0 to t, we have e to the 2u cosine squared e to the u plus e to the 2u sine squared e to the u plus 3e to the 2u. And of course, you get the square root of this and then the du. And this guy here plus this guy here, it's just e to the 2u. So we have the integral from 0 to t of e to the 2u. And then here you have 3 e to the 2u. And then you get the square root of this and then you have the du. And of course, e to the 2u plus e3 plus 3 e to the 2u, that's 4 e to the 2u. So this is simply the integral from 0 to t of 2 e to the u du. And this is what? 2 e to the u evaluated from 0 to t. So this is 2 e to the t minus 2 e to the 0, which is just 2. So this is our s of t. S of t, it's equal to 2e to the t minus 2. So the parametrization, okay? So let me rewrite that one here again. So S of t, this is 2e to the t minus 2. So we want to write t in terms of s, okay? And then we will replace that in here. And then you have the parametrization or reparametrization with respect to the arc length. Okay? But instead of solving for t, I'll just solve for e to the t because anyway, we have here e to the t, e to the t, and e to the t. So this guy here, we will have 2e to the t equals s plus 2, or e to the t, this is equal to s plus 2 over 2. Therefore, we have r. And then let me put the asterisk, meaning we are reparametrizing this. Okay, so in terms of s, this is now sine s plus 2 over 2 I hat plus cosine s plus 2 over 2 j hat plus square root of 3 s plus 2 over 2 k hat. And this is our answer. Okay.